In this lesson, you are going to learn how to look at the information given to us on the periodic table, on the back side of the periodic table, and interpret in a way that we can solve for any acid and base problems. So first of all, we have our Ka right here. Well, from here, you can actually interpret in terms of a reaction. So notice how we have our acid right here. That is our Bronsted acid right there, okay? Bronsted-Lowry acid right there. And that acid, when you put in water, it will donate its hydrogen. That's the definition of Bronsted-Lowry acid. It donates a hydrogen. And in the end, we would have this conjugate base, okay? And notice how it's missing a hydrogen. And this is a conjugate pair. In the process, we produce this hydronium ion, which is equivalent to H+, okay? So keep that in mind. And in most cases, you would write H+ instead of H3O+. Where if we have Kb, of course, this is our reactant, right? Our base. And our base, when we put in water, remember the acid donate hydrogen plus? Of course, the base would do the opposite. It would accept an H+ from the acid. In this case, water is functioning as an acid, and in the process you create a conjugate acid. And how do you know? See how this base having an extra plus right there, and then what we have in the end is OH- produced from the base and H3O+ produced from the acid. And if we are given our Ka values as well as the concentration for this, okay, so if this is given to us and if this is given to us, we can actually solve for this right here, the H+, if we're given Ka and the concentration of the acid. Or for the Kb, we can actually solve for OH- if we're given Kb as well as this is given to us, okay? To do that, you use the ice table, of course. In addition to solve for the concentration of H+ or OH-, you can actually solve for pH or POH. And what does the letter P represent? Well, if we look at this right here, the letter P basically represents negative log. So if pH right here, that is basically negative log of the concentration of H+. And if we have POH right here, that is the negative log of the concentration of OH-, okay? Now, if we are not given the Ka or the Kb, but we are given the pH or POH, we can actually solve for the concentration of H+ or OH from pH or POH. And basically, all we have to do is to cancel out the log. And the way it works like this, if we have a base log to the base, which in this case, that log right there is base of 10. So we have 10 to the power of log base of 10. That is equal to 1. So what's happening here is that if you are given pH, to find the concentration of H+, all you have to do is take 10 to the power of negative pH. For OH, we're going to do the same thing, but we are going to take 10 to the power of the negative POH, and that gives us a concentration of OH. So all this information are given to us on the back side of the periodic table. See right there? But how you interpret is what makes it challenging. Then we also have how is Ka related to Kb? It's basically Ka times Kb equal to Kw. Now what does W represent? That is the dissociation of water. And it is actually given to us, water is 1 times 10 to the negative 14. Okay, and this happening at the normal room temperature, which is 25 degrees Celsius. So be careful of that. And from there, we are also able to find for the concentration of H+ or OH- given a Kw. So there are a lot of information that you need to put together to get what you need, okay? So don't rely on memorizing one thing, but learn how to use the back side of your periodic table and use what you need. But before we start solving a problem dealing with acid and base, we have to look at one of the most important equations of all. It is the Henderson-Hasselbalch equation. This equation right here. We have pH equal to pKa plus log of the conjugate base over the acid. And notice how this is acid right there, right? So the acid is on the bottom. And that's how I remember, Okay, it happened in a conjugate pair. The one that you look at for Ka, that's your acid, so that's what you are comparing to. Where if we look at Kb, guess what happened on the bottom? B is for base, so the base is going to be on the bottom. So notice how B is for base, and base is the measure of concentration of OH minus, and that's why we have POH. And look what happened. We have the base, and this will be your conjugate acid right there. So that's the information that we can get from this Henderson-Hasselbalch equation. Now, how do we use it? If you look at the two equations of the Henderson-Hasselbalch equation, there are two possible changes that we can make to a solution. And one of the changes that you can do to a solution is you can actually add in the conjugate base in a form of a solid salt. And when you do that, right, the salt, when it touches the water, it will dissociate into ions, and this one right here is going to add to this, right? Now, it's only adding to the conjugate base. It doesn't do anything to the acid, okay? So keep that in mind. That's why it only add to the conjugate base. But here's another situation where you can change the solution of a buffer. Well, what you can do is, what happens when you're adding a strong base in an acidic solution or a strong acid in a solution? Well, the word strong, that is 100% dissociation, okay? Now, if you're adding a strong base, what does a base do to the acid? Of course, it's going to react with the acid. Even the acid is weak. So what's that going to do is that the number of mole of base that you're adding is going to be subtract from the acid because it's reacting with the acid. But when you subtract, what is that really happening? It's basically you really reacting with the acid. That means you actually use up the acid on the reactant side, right? So now the acid on the reactant will be less. But what are you making? Of course you're making the product. What are you making in this case? Remember, the acid will dissociate to make a conjugate base. So in this case, the green part is what's tricky. You actually have to subtract from the acid, but that same amount is going to be added to the conjugate base. Because now those acids will react with a strong base to make the product. And this is all relative in terms of mole. You cannot do subtraction in terms of molarity. It has to be converted to mole first. And how you do that? You take the volume times the molarity. That gives you a number of mole. Just keep in mind that the volume is in liters, okay? And the same thing for POH. You can add in the salt, and that will only affect the conjugate acid. Or you can actually, in this case is a base, we can add in a strong acid, and this strong acid will 100% dissociate. That means break into ions, 100%, all of it, and then they're going to react with the base. And basically this acid is going to react with the base. Of course now the values of the base is going to go down, and that's why we subtract it. And in the process, it's going to make the product. So we subtract from the base, but we're going to add to the conjugate acid right there, okay? And that would, in the end, affect our ice table. But before we actually start solving the problem, we need to realize that the change in X is really, really small. So we can actually assume that the concentration of the initial is about, or actually equivalent to, the concentration at equilibrium. And I'm going to show you how that works, okay? Let's start solving one problem. In this case, what we have here is a reaction of an acid right there, and it's making a conjugate base right there, and producing this H+. If I were to rewrite this with water, okay, it would look something like this, and this would happen to be H3O+. Okay, that's another way of writing it. So it's giving us our Ka, nothing else. And then it gave us a name, is ionized in water, and so on. And the problem asks us to solve for the pH of a 0.2 molarity solution of propanolic acid. Well, when it comes to pH, guess what do you need to have? The concentration of H+. But we don't know anything about H+, except that it is in this reaction. And from this reaction, we have our Ka. So we go back to this right here, right? Look at our Ka. We have our concentration of H+ right there. So let's see if we can write this as an equilibrium constant. Well, of course, that's pretty easy. So Ka is equal to the product, okay, over the base. And this is our concentration of H plus right there, which allows us to find pH, okay? And that is over your reactant. Now, first of all, if we look at the ice table, okay? Well, initially, what we have here, it says that it is 0.2 molarity. So that is your initial concentration of the acid right there. And that's in term molarity. Well, of course, this solution, and based on the problem, we haven't made any product yet. So this is the initial molarity of this solution, and we haven't made anything yet. And of course, for the product, we will have 0 because nothing has happened yet. And then we have the changes because this is a weak acid. We don't know it's going to react completely or partially. We just know it's happened to some extent, and we use a variable minus x over here. So if this is being used up or dissociate, it's going to make the product in the same amount in terms of x. Because it's a 1-to-1 ratio. That's why we have x, x, x. Then we have our equilibrium where in addition to the initial, now you have changes over time. So we have 0.2 minus x, and we have x and x. And what does x really represent in this case? X is actually equal to C3H5O2 minus, or the concentration of H plus. So be careful. Sometimes they could ask you for a certain amount of information that is not really relative to pH. So be careful with that, okay? So now let's plug this in. We have a Ka, which is 1.34 times 10 to the negative 5. Notice how I couldn't use the Henderson-Hasselbalch equation in this case, but I have to use this one. That's because we don't know what is the concentration of the conjugate base at equilibrium going to be. It is in terms of x, so we have to solve it using your Ka, okay? So we have that in this case. So this is equal to x times x, and this is equal to 0.2 minus x. So we can have pretty much x squared divided by 0.2. We can ignore this, okay? And x turned out to be, how do you solve for x? You multiply that and you take the square root of it. So x is going to be the square root of 0.2 times 1.34 times 10 to the negative 5th. And that is going to be 1.63 e to the negative 3 molarity. And that is equal to the concentration of this as well as the concentration of H+. Now we have a concentration of H+, what can we do? We can now solve for pH. And basic pH is just basic negative log, okay? So in this case, I'm going to write right here. So we have negative log of that. H+, in this case, is equal to negative log of 1.63 e to the negative 3. And that gives us our pH. And that gives us our pH 2.79. Now, if this were to be a basic solution, of course, you will use Kb and solve for the OH minus, okay? The same thing. In addition to asking for pH, they can ask you a lot of things. They can ask you the concentration of the conjugate base, the concentration of H+, and all those things are fair game on the AP test. Or they can ask you for the POH. And what does POH have to do anything with pH? Well, right there, pH plus POH equal to 14. So what we have here is POH equal to 14 minus a pH, which is 2.79. And what do we have? We have 11.21. Now, what if I want to make this extra and want to solve for the concentration of OH? So if I would want to solve the concentration of OH, I would have to do what? Notice how we can ask so many different questions on the same problem, okay? Well, let's go back to this. Again, all you have to do is take 10 to the power of the negative POH, and that is 11.29. And that would be your concentration right there. Boom, done. Okay? That's pretty easy, isn't it? So keep that in mind, okay? Now let's get to, this is only one ice table. But before, you learn how to use an ice table on another ice table. Now, we're going to look at the Henderson-Hasselbalch equation, how we can eliminate the second ice table, okay? And that's what the beautiful part about this. Well, in this scenario, I'm adding 0.75 grams of sodium propionate. And if you look at this, that is the salt that you can add into solution. In this case, the solution is 100 milliliter of 0.2 molar solution of the same acid, okay? Now we actually have the volumes of it. Assume that no change in the volume of the solution occurred. That means you add in the salt, and that salt is so small, it doesn't change any volume. So the question is now calculate what? What are we trying to calculate? Calculate each of the following. Well, I forgot. Let's calculate pH. How about that? Let's look at pH. How is this going to affect our pH? So we know based on the Henderson-Hasselbalch equation that we adding the salt is affecting the conjugate base right here. Okay, that's it. It doesn't affect anything else. So let's see that in terms of the ice table. Well, remember your ice table in terms of your reaction. We have this right here. It's given to us right there. I'm going to write it down again. One thing you have to know that this right here, this problem right here, we are making an assumption that this acid has not reacted with any water yet, okay? So we can actually ignore this, okay? Based on the Henderson-Hasselbalch equation, we are only focused on two things, and that is the concentration of the conjugate pair. If it's pH, I'm looking for the concentration of the Bronsted-Lowry acid and its conjugate base, okay? Where if pH, I would look at the Bronsted-Lowry base and its conjugate acid. Because I'm adding the salt to it, of course it's going to change the concentration of the conjugate base right here, which is this one right here. And if you don't know what I'm talking about, look at this salt right here. If we split this up, we know this dissolves in water. That will give you minus and that will give you plus. Doesn't that look like this? Okay? Of course, this is not going to affect any of this right here. So now, let's look at this problem. We know for sure based on the ice table, notice how I have eliminated the majority of the reaction and just focus on the Henderson-Hasselbalch equation. Well, initially, this right here has what? 0.2 molarity, right? But when we calculate our changes, it has to be in terms of mole. That's the most important thing. It has to be in terms of mole first before we convert into concentration. So how can I take this molarity and volume, make it into mole? Well, in this case, we have 100 milliliter, and we take that and we multiply. This can be converted to liter, and basically 0.1 times 0.2, and we take 0.1 times 0.2, we got 2e minus 3, okay? Then over here, we are given in terms of grams of this compound. Well, if we look at this, we have 0.75 grams of NaC3H5O. Well, what can we do? Well, that's pretty elementary, right? We just take this, times the molar mass, which in this case is 96 grams, and that is relative to 1 mole. Notice how the grams cancel out. And this gives us 7.81 e to the negative 3 moles of NaC3H5O. Well, we only focus on this part. We don't care about the Na, but this is a 1-to-1 ratio. So what can we do? So in this case, if we look at this right here, think of this as a polyatomic ions, okay? So we have 1 moles of that compound. And in that 1 moles of this compound, how many moles of this do we have? Of course, it's 1. And that's why this cancels out and give us 7.81 e to the negative 3 moles of C3H5O. And that's how you take this salt and convert it to the moles of the conjugate base in the solution. Well, we learned that X changes, well, this right here, is gonna be really small. Okay, the same ice table, but now we can actually skip the ice table if we use our common sense. We learned that X is so small that we can actually ignore it. And all you have to do now is take this, ignore all these changes, take this and convert it back to molarity. And how do you do that? You divide it by the new volume. Notice how I changed this value. It was e to the negative 3. I double checked the math. 0.1 times 0.2 is e to the negative 2. So again, we go back and look at the moles, and now we convert back to molarity. Because the same volume, the molarity was not going to change for this acid right here. So it's going to be 0.2 molarity again. But for this guy right here, for this conjugate base, we would have to divide by 100 milliliter. And that in terms of liter is actually equal to 0.1, okay? So keep that in mind. And that would give us a new initial values for this. And this gives us 7.81 e to the negative 2 molarity. And that is the concentration of this right here. And remember how I cross out C and E? That's because we assume that the change in X is so small and that the initial concentration is actually equal to the equilibrium concentration. So we have all the condition or all the values for the Henderson-Hasselbalch equation. We have our Ka, we have our concentration of the acid after adding the salt in, and we also have the concentration of the conjugate base after adding in the salt. So let's plug this in. So let's plug this into the Henderson-Hasselbalch equation. So here it is again. Our Ka from up here, it is given to us 1.34 times 10 to the negative fifth. So we have negative log, that's coming from the letter P, of 1.34 times 10 to the negative fifth, okay? And plus log, okay? Now remember to put parentheses in this case. If I were to plug this into a calculator, it would look something like this. Parenthesis, log, what's the concentration of the conjugate base? Is 7.81 e to the negative 2 divided by, what's the concentration of the acid? 0.2. That's again because we know that the change in X is really, really small. And why is that possible? Because we assume that the change in X is really small. And that divided by 0.2. And in the end is giving us 4.46. And that is our pH. Isn't this a lot faster and nicer? And what if I want to calculate for pOH? Oh, that's easy. So pOH is equal to 14 minus 4.46. And that would give us 9.54. Now, what if I want to find the concentration of OH minus? How about that? That's even easier. I just take 10 to the power of negative of the pOH, which is 9.54. Isn't that easy? Now, what if I want to find the concentration of H plus after adding in the salt? Well, that's pretty easy too. So we have H plus equal to 10 to the power of negative pH, so it's negative 4.46. As you can see, there are multiple questions that can, as you can see, I can ask you multiple questions about the same scenario, okay? Now, well, let's look at a different scenario where now, what is the pH if we add in 15 milliliter of 0.1 molarity, okay, that's molarity, my bad, right there, of NaOH, to the same solution, 100 milliliter solution of this same acid. How is that going to affect anything? Before we start this problem, we have to realize what's happening when we add a base to an acid. Of course, it's going to react. And is this a strong base? Yes. So therefore, it's going to be 100% dissociated. And of course, we are using the Henderson-Hasselbalch equation to solve this problem. But before we can apply the Henderson-Hasselbalch equation, we have to figure out what is really happening to the concentration of the acid and its conjugate base. And I'm going to write the reaction again. In this case, I'm going to show you with water, okay? And again, we have to make an assumption that this has not been reacted with water yet. So we can just get rid of that. Before we even consider what happened when it's interacting with water, we need to look at what happened when we have NaOH adding to it, okay? So if this is an OH, which is a base, what is it going to react with? Well, this is a conjugate base, and that's an acid right there. Of course, this OH is going to add over here. It's going to react with the acid, okay? So in this case, our OH minus is going to be right there. So what we're going to do is this. Remember, this is a strong base. So it's going to completely dissociate and react with this. Now, can we solve for this in terms of mole? Every time we calculate for changes, it has to be in terms of mole. Well, that's pretty easy. We take 15 molarity. Well, to convert this to mole, it's pretty easy. We take the volume times the molarity. Well, convert to liter first. We have 0.015 times 0.1. And that gives us 1.5 e to the negative 3. Okay, that is the number of moles of OH minus. Okay, and what about this right here? Well, we have our volume and the molarity. Of course, we can find moles from there. The same thing. We take our volume, convert to liter, which is 0.1 liter, times the molarity, which is 0.2, and give us a number of moles, which is 2e minus 2. So this is the number of moles of the acid right there. And of course, on the product side, we haven't made any of the conjugate base yet because nothing has happened yet. That is our initial. That's why we use the term initial. It's just the starting. Now the changes. Of course, this strong now the changes, of course, this right here, strong base, will be completely ionized. So we're going to use all of it. I'm going to minus 1.5 e to the negative 3. And that will give our equilibrium, makes sense, is equal to 0. We're going to use all of this. All this is going to react with this right there. So if we are reacting with this, this is going to get used up on the reaction side, right? So we're going to minus 1.5 e to negative 3 as well. So we minus this, and at equilibrium, we would have 2e minus 2 minus 1.5 e minus 3. And this gives us 1.85 e to the negative 2. And of course, this is 0. Now, if this is reacting with a strong base, of course, whatever being used up over here, based on the ratio of 1 to 1, and based on the coefficient 1 to 1, we know that whatever is making right here is going to be the same amount as going to make here. So we would have 1.5 e to the negative 3, and now our conjugate base is no longer 0, it's going to be 1.5 e to the negative 3 moles, okay? And that is how adding a base affects the concentration of the whole entire solution. And these two values right here, they will become the initial values when we take account of the waters. So what we have here, of course, we need to convert this to molarity. So we have the same thing. I'm just going to focus again based on the Henderson-Hasselbalch equation. I just care about the acid and its conjugate base. So I'm going to focus on those two things only. Okay? And that's going to make our conjugate base, in this case C3H5O. Notice how I ignore everything else. Okay? So this is what in terms of mole. So I have to divide this to get the molarity. And what is the new volume in this case? Well, let's write this in terms of mole. Divided by the new volume is 100 plus 15 milliliter. And if this convert to liter, we would have 0.15 liter. And give us our molarity turn out to be 1.23 E minus 1 molarity. Okay? What about this right here? What about the conjugate base? Well, this is your mole initially right now. It will become the initial right here. So 1.5 e to the negative 3 divided by the volume, which is the same volume as this one because they are in the same container. So 15 milliliter, and that will convert to 0.15 liter and give us our concentration. In this case, plug into a calculator, we have 1.0 e to the negative 2 molarity. Now we have the concentration for the Henderson-Hasselbalch equation. Now we have the concentration of the conjugate pair in the Henderson-Hasselbalch equation. So negative log, the same Ka, which is negative log of 1.34 times 10 to the negative 5. And that is the same Ka that we had before right there, okay? Right here. So that's going to be plus log of, again, I'm going to plug like I'm plugging the calculator just because. In this case, the top numbers is your conjugate base here, 1.0 e minus 2 divided by 1.23 e to the minus 1. We have 3.75 equal to our pH. And the pH turned out to be 3.75, which makes sense because if we look back at the very beginning where we haven't added anything to it, the solution itself, the pH is 2.79. That's acidic. That is more acidic than this. So by adding the base to it, look what happened to the pH. It could rise. That means it go up. The higher the pH, the more basic it is. And what if I want to solve for pOH? Of course, pOH would be 14 minus 3.75. And that would give us what? 10.25. Now, what if I want to solve for the concentration of H plus right here? Well, if I want to do that, same thing again. Concentration of H plus is equal to 10 to the power of negative pH. In this case, is 3.75. Boom. Why do I want to solve for the concentration of OH minus? Well, same thing. 10 to the power of negative pOH, which is 10.25. Let's see how easy that is. So, learn how to use the Henderson-Hasselbalch equation if you have a hard time using two or more ice table, okay?